Rush hour. The entire rail network freezes. No accident, no visible damage, just a sudden, total standstill. The train was so advanced that not even its creators could get it moving again. Promised as the future of transport, its technology was so intricate repairs became impossible, leaving passengers stranded and engineers helpless. How does a marvel of innovation become an unfixable liability? The answer starts exactly where the chaos began. At 8:13 in the morning, the train's digital control system displayed a single word across every onboard monitor: hold. Doors locked, lights flickered, and the cabin temperature began to climb as ventilation stalled. Hundreds of commuters, packed shoulder to shoulder, pressed against the glass, waiting for an announcement. None came. Across the city, station platforms filled with crowds who watched arrival times jump from minutes to blank screens. Operators at the central control room stared at a wall of frozen data feeds. No alarms, no visible cause, just a network-wide paralysis. Within 10 minutes, the ripple spread beyond the train. Dozens of other services halted behind the motionless flagship, creating a chain reaction that forced dispatchers to divert or cancel every rush hour route on the line. Emergency protocols kicked in, but the automated systems refused manual override. Engineers on the ground, some with decades of experience, tried to access diagnostics but were locked out by encrypted error codes. Inside the immobilized train, phone signals jammed as hundreds tried to reach work or family. The intercom crackled with pre-recorded messages about temporary delays, but no one could say what had gone wrong. With no physical evidence of a crash, fire, or sabotage, passengers grew restless. Some pounded on doors. Others searched for staff, only to find conductors as confused as everyone else. By 8:45 in the morning, news outlets picked up the story. A state-of-the-art train, hailed as the future of urban transport, now sat powerless in the heart of the city. The rest of the network, designed around its flawless operation, was gridlocked. The train's own engineers, summoned from the manufacturer, arrived with laptops and keycards, yet every attempt to restart the system failed. The city's morning had ground to a halt, not from disaster, but from a silence no one could break. At launch, the train's creators promised a revolution. Full automation, no human driver required, would deliver precision, safety, and efficiency beyond the reach of traditional systems. The press release called it a single-vendor solution, where every component, from propulsion to passenger information, came from one tightly integrated stack. The rationale was simple. Vertical integration would eliminate the patchwork of suppliers and legacy interfaces that had slowed down rail innovation for decades. Every sensor, every circuit board, every line of code was custom-built to fit this vision. The lead systems architect, Dr. Lena Kovacs, described the approach in a rare interview. She explained that they wanted a train that could think for itself, not just respond to signals, but anticipate failures, reroute power, even self-diagnose and schedule its own maintenance. To do that, they had to design every layer in-house. No off-the-shelf parts, no compromises. The ambition was clear in the technical briefings. Instead of analog controls and manual overrides, the design relied on a digital nervous system, an array of redundant processors, high-speed data buses, and machine learning routines that governed everything from braking to climate control. Predictive maintenance algorithms would flag issues before they became problems. Modular hardware meant upgrades could be rolled out by software update. Operators were told that downtime would become a thing of the past. This bold integration came with trade-offs. The system's complexity was justified as a necessary price for progress. Specialists insisted that only by controlling every variable could they guarantee the reliability demanded by a 21st century city. Maintenance teams would be retrained, manuals rewritten, old assumptions discarded. The The promise was seductive, a train immune to the failures that plagued its predecessors. On opening day, dignitaries and journalists toured the spotless cabins and watched as the train glided out of the station, guided not by a human hand but by millions of lines of code. The future, it seemed, was finally here. At the heart of the AE-1 sat a control system unlike anything seen in previous generations of trains. Instead of a central switchboard or a handful of programmable logic controllers, the designers built a distributed brain called the Train Control and Management System, the TCMS. This network spanned every carriage, with redundant processors linked over high-speed Ethernet, running a proprietary operating system. Each subsystem, brakes, doors, HVAC, traction, reported its status to the TCMS, which coordinated every action in real time, down to the millisecond. The architecture promised near-perfect efficiency. Predictive maintenance algorithms sifted through a constant stream of sensor data, flagging anomalies before they caused breakdowns. If a door motor drew too much current, the TCMS would schedule a service call. If temperature drifted in a carriage, the system would auto-correct airflow. But this intelligence came with a catch. All diagnostics and all control routines were locked behind vendor-licensed software. Only authorized tools could access the encrypted logs, and those tools required digital keys issued by the manufacturer itself. Even the basic act of troubleshooting required a laptop loaded with proprietary software, connected to a secure port, hidden behind a locked panel. The TCMS refused to reveal raw error codes or subsystem states without the right credentials. Maintenance manuals described processes in broad strokes but omitted the inner workings of the software logic. For each firmware update, only the manufacturer's engineers could review the source code or adjust the predictive models. This digital nervous system, by design, eliminated the possibility of improvisation. The system's interdependency meant a fault in one module, for example a glitch in the door logic, could ripple through the network, triggering traction interlocks or disabling braking subsystems. A software bug could immobilize hardware, and a single corrupted data packet could confuse the entire train. It was a marvel of integration, but it left operators with no way to isolate or bypass faults. The AE-1 could think for itself, but only on its own terms. Long before the network-wide paralysis, field reports from maintenance crews started piling up. The first entries in the incident log were easy to overlook. A door refusing to unlock on a cold morning, a brake that held too long at a suburban platform, fans cycling off for no clear reason. Each time, the train's onboard system flagged the issue. But the error codes were cryptic strings of numbers and letters that pointed only to a generic subsystem fault. Replacement parts, when needed, had to be ordered directly from the manufacturer, with delivery times stretching from days to weeks. One winter, a depot chief scribbled in his maintenance notebook, "Brake lock on car 4 again. Reset does not hold. Waiting on module from Derby." The same note appeared 3 times that month, each time with mounting frustration. The official maintenance protocol required connecting a specialized laptop to the train's diagnostic port. Only a handful of engineers had the right credentials to access the logs. Even then, the software offered little more than a list of unresolved alerts. When a traction motor overheated during a routine run, the depot team found themselves staring at a screen that simply read, "Subsystem unavailable." Contact vendor. Parts delays became routine. A single custom circuit board could sideline a train for 1 week. Technicians swapped modules between units, hoping to keep at least one train running. But the backlog grew. Early warning signs, overheating, unexplained resets, odd noises from the undercarriage were logged, reset, and logged again. Each incident on its own seemed minor, The train always returned to service, and passengers rarely noticed more than a few minutes' delay. In the maintenance bay, frustration simmered. The depot chief later recalled that they kept thinking it was just teething problems. Every new system has bugs, but the bugs never really went away. They just kept coming back, a little different each time. The warning signs were there, buried in the logs and the notebooks, waiting for someone to connect the dots. A forensic review of the AE-1's collapse begins with a single event buried deep within the system's digital logs. At 8:13 and 4 seconds, a voltage spike registered in the door control module of Car 3. Within milliseconds, the train control and management system, called TCMS, flagged an anomaly and isolated the affected circuit. But instead of containing the fault, the isolation triggered a software cascade. The TCMS, programmed to prioritize passenger safety, instantly locked all doors and cut traction power not just in Car 3, but across every carriage. The system's global interlock protocol activated, halting propulsion, brakes, and ventilation in a synchronized freeze. Investigators later traced the sequence. The initial spike propagated through the high-speed data bus, tripping redundant processors in rapid succession. Diagnostic packets flooded the network, each demanding a subsystem check. The predictive maintenance algorithm, overwhelmed by conflicting inputs, flagged every subsystem as potentially compromised. Within 12 seconds, the train's digital nervous system had triggered a full lockdown. The ventilation shut down, lights dimmed, and the emergency battery backup failed to engage. Its activation logic locked behind the same frozen software routines. Central Control attempted a remote restart, but the encrypted communication channel rejected all external commands. The TCMS fail-safe routines, designed to prevent unauthorized access, now blocked even authorized engineers. No manual override existed for this scenario. On board, the digital interlock prevented any attempt to open doors or reset systems. The event logs show a relentless chain: error code 0x1001, door fault; 0x2002, network latency; 0x3003, diagnostic overload. Each code echoed through the system, compounding the paralysis. An independent safety investigator reviewing the logs described the event as a textbook cascade failure. A minor electrical anomaly, instead of being isolated, rippled through every layer of the train's architecture. Within less than 15 seconds, a single point of failure had immobilized not just one train, but the entire network built around it. The AE-1's complexity, intended as its strength, had become its undoing. Months after the AE-1's debut, the cracks in its support system became impossible to ignore. Every key component was custom-built and tied to exclusive contracts with a single manufacturer. When a circuit board failed or a sensor glitched, there was no warehouse full of spares, just a requisition form sent back to Derby, and a wait that could stretch from weeks to months. Some parts were so specialized they required small batch production runs, with lead times measured in quarters, not days. If a supplier missed a deadline, the entire repair queue froze in place. Even the tools needed for diagnosis were not standard. Maintenance laptops had to be loaded with vendor-issued software, activated by digital keys that expired after a set number of uses. Losing a key meant waiting for a new one to be couriered from the manufacturer, sometimes across borders. Under the terms of the license, only certified engineers could access the most sensitive diagnostic routines. Depot chiefs described the process as repair by permission slip. Every intervention required approval, and every login was tracked. The knowledge gap widened with each passing year, and the shortage of expertise became obvious. Training manuals arrived late, often incomplete, and written in technical language that assumed prior experience with the system's architecture. Most local technicians were trained on older models and found themselves locked out, literally, by encrypted panels and password-protected interfaces. Only a handful of specialists, often flown in from the manufacturer, could navigate the maze of software layers and proprietary codes. When they left, they took their expertise with them. Routine maintenance became a negotiation. Operators juggled schedules around the unpredictable arrival of parts and the limited availability of credentialed engineers. Some trains sat idle for months, cannibalized for parts, to keep others running. The promise of seamless, self-diagnosing technology had given way to a reality of bottlenecks and blind spots. What was intended as a closed, optimized system now felt like a fortress. It locked out not just intruders, but the very people tasked with keeping it alive. Technical teams cycled through every tool in their arsenal. The first fix attempted was a firmware rollback, meant to bypass the network latency that had paralyzed communications between the train's processors. But the system's layered encryption rejected the old code, flagging it as a security risk. Instead of restoring function, the attempt triggered a full gateway crash, cutting off even basic diagnostic access. Reverse engineering the affected modules took days, with specialist contractors working in shifts. But each workaround only revealed more dependencies. One subsystem would reboot, but another would lock up, waiting for a handshake that never arrived. Specialists were flown in from the manufacturer's European headquarters, but even they struggled to navigate the maze of proprietary interfaces. Every patch required approval from the original software architects, and each intervention risked voiding the warranty or introducing new faults. At one point, a replacement circuit board was couriered overnight, only for engineers to discover that its firmware version was incompatible with the rest of the train's network. The result? A new error code, a fresh cascade of failures, and another round of finger-pointing between operator and supplier. The chief financial officer of the transport operator summed up the mood in a terse memo. "Every repair attempt increases our exposure. We're burning cash just to stand still." As the repair bills mounted and the train remained motionless, it became clear that no combination of parts or expertise could bring the system back. Each fix made things worse, not better. The AE1 was now less a train than a cautionary tale, an asset too advanced to operate, yet too expensive to abandon. Operators weighed every option before conceding defeat. With each day the AE1 sat idle, losses mounted, including ticket refunds, substitute buses, and idle staff pushing daily costs past €1 million. The repair budget ballooned as consultants, engineers, and replacement modules arrived, only to find each fix unraveled another layer of complexity. After months of fruitless effort, the board approved the unthinkable. The entire fleet would be retired, years ahead of schedule. Accountants tallied the numbers. Hundreds of millions in sunk costs, written off in a single quarter. Trains that were meant to serve for 30 years had lasted less than 5 years. The replacement order went to a manufacturer offering a proven modular design, nothing proprietary and nothing experimental. These new trains arrived with thick paper manuals and a warehouse full of standard parts. Mechanics who had spent months locked out of encrypted panels now returned to familiar tools and off-the-shelf spares. The contrast was impossible to ignore. While the cabins of the AE1 were cut apart for scrap, older models, built decades earlier, continued to run daily, maintained by crews who knew every bolt and relay. The lesson played out in balance sheets and maintenance yards alike. Complexity had promised a leap forward, but the cost of surrender was paid in both money and trust. Around the world, engineers now face rising pressure to deliver smarter, faster, ever more connected systems. Yet according to the International Energy Agency, half of all critical infrastructure failures today are linked to unmanageable complexity. As we rush toward automated futures, the real question is not how advanced we can build, but whether we can still fix what we create when it matters most.